Homework 6. Question number 1. What is the steady state approximation and when is this approximation employed? Steady state approximation applies to a consecutive reaction where the concentration of the intermediate remains constant, or the rate of this concentration change is 0. Question number 2. For the following overall reaction, is it a first order or second order reaction? Because this is an overall reaction, we cannot predict the rate law. We have to predict a rate law based on the reaction mechanism. Question number 3. Using steady state approximation to derive rate law of this overall reaction where the mechanism is given. To derive rate law, we choose either reactants or product. But when we derive rate law, we have to look at the mechanism, not the overall reaction. All right, let's choose product to derive rate law. In the mechanism, only the last step involves the product. And this is the first order reaction because the reactants is the concentration of intermediate. And so the rate law for product is Kb times I. Now, because I is intermediate, we need to express this concentration as a function of either reactants or product. And this is when we use a steady state approximation. We write rate law for this intermediate, and we let this to be 0 to solve concentration of I and put back into this equation. According to the mechanism, this rate law for the I involves 3 processes. The first step, forward reaction. All right, so Ka times the reactants for the forward reaction is A and B, second order reaction. And this step process can produce I, so it's positive. And the reverse reaction for the first step consumes I, so it's negative Ka prime. The reactants in this process is I for the reverse reaction. And the second step to produce P also consumes I, so it's minus Kb times I. Okay, so that's the second step. All right, so that's the rate law for the intermediate, and then let this to be 0, and we solve the concentration of I. All right, so this equation is equivalent if we write as A, B equals Kb I plus Ka prime I. All right, because we move this 2 to the right side, so both becomes positive. And this can be factor the I out, so Kb plus Ka prime. All right, and then the concentration of I can be calculated by both sides divided by Kb plus Ka prime. And that's the concentration of I. Now put back into this equation. So here is the final solution for the overall reaction rate law, which is first order with respect to A, first order with respect to B, and the second order overall. Question number 4. What is the pre-equilibrium approximation and under what condition is it considered valid? Now, pre-equilibrium approximation applies also to consecutive reaction. Well, in this approximation, the first step, AB goes to I, and I also go back to AB, is assumed to be in equilibrium. This assumption is valid when this reverse reaction, Kr, is much greater than Kp to produce the product. Under this condition, ABI may reach equilibrium. Using this approximation, we can write the equilibrium constant equals I divided by Bc. Now, equilibrium constant can also be written as the forward rate constant divided by reverse rate constant. So in this way, we can also solve the concentration of I, just as we use the steady state approximation. Question number 5. Considering following mechanism, what is overall reaction? Okay, let's look at the mechanism. In the first step, B is the product, but in the second step, B is used as a reactant. So this B should cancel each other. And so we add these two reactions together, and we give 2A as a reactants, and the product is 3C, and that's the overall reaction. In B, if the first step reaches equilibrium, and the second step is the slow rate determining step, derive the predicted rate law. So this is asked to use the pre-equilibrium approximation, okay, where this is in equilibrium, to derive rate law. So we are going to do it in the next slides. So in this mechanism, the first step is in equilibrium, and the second step is slow, which is a rate determining step. And therefore, the overall rate law can be written as just the second step, K2 times reactants AB, which is the second order reaction. And this is a rate determining step. Now, because the overall rate law involves an intermediate, we need to express this intermediate concentration as a function of reactants or product. We use pre-equilibrium approximation for the first step, and we write a rate equilibrium constant for the first step as a product divided by reactants. All right. Now, in this case, equilibrium constant can be expressed as the rate constant. So forward divided by reverse, and we can solve concentration of B, all right, as K1 might divide by K minus 1, A divided by C. And this goes back into this equation. Okay, finally, we have this equation shows that the overall rate law is the second order with respect to reactants, all right, and inversely proportional to the product.